Yes, so today I'm going to show you how to use a library which is called Tree-Sitter, and which I discovered not so long ago, and which I found pretty useful for different use cases. So what is a Tree-Sitter? I took the description from their website. It's a parser generator and a parsing library. So a parser generator is a tool that takes a definition of a language, for instance, a programming language, and outputs a parser for this language. And a parser takes the source code of the language, and it outputs a syntax tree of this source file. So concretely, if you have a statement, here it's a Python statement, for instance, like print a function with 2 arguments, hello world, what this library and more generally what a parser does is that it goes from this statement to a tree, which represents the syntactic element of this block of code, right? And in particular, this library that I'm sure we'll be discussing today, they output what's called a concrete syntax tree, which means that we have all the elements. So we have even, like, what's not meaningful from a code point of view. So we have even like the parentheses or the quotes and so on, but we will discuss that again later. So it's a library that goes from this to this. And once we have this tree, it's much easier to manipulate from a code point of view and to, perform analysis on the code and so on. So what makes Tree-Sitter different from other libraries that does the same thing, that solves the same problem? At first, Tree-Sitter was created for text editors. It was created for the Atom text editor, which was made by GitHub. Unfortunately, it's deprecated. It's not maintained anymore. But at first, it was created for text editors. And most of text editors, they do syntax highlighting, right? So you have code and you want to put colors on the keywords and so on of the code. And the way it used to work, and most of them work, is they use just regular expressions to match keywords. And they say, okay, if the word is like function and there's nothing before, then highlight this word in blue. If it's the keyword like async or await or def or whatever, then put another color and so on. So this is pretty easy to write definition for a language and to have syntax highlighting, but there's no semantic understanding of the code. The text editor can put colors, but it has no understanding that this function has 2 arguments and or that this function belongs to a class and so on. So Tree-Sitter was created to be able to use syntax trees for syntax highlighting and other purposes. But for this, you need something that is fast. And when you use a text editor, every time you press a key, well, you need to recompute the syntax highlighting. And in this case, you need to recompute the whole syntax tree. So Tree-Sitter was designed to be very fast. And in particular, what they call incremental parsing, which means that you can tell it, I know that only these bytes of the source code have changed. So recompute, only the part of the tree that have changed. So that makes it fast. It was designed to be able to parse, a lot, or maybe any programming language. Also to be robust, because some languages, when they encounter a parse error, for instance, in C, like if you use a C compiler and you forgot, a semicolon somewhere, it's just going, to break at this point, and it's not going to try to parse the rest of the code, because most likely the code is invalid if you forgot a semicolon. But for a code editor, you still want to be able to highlight the rest of the code, even if there's an error in the middle. You don't want to have colors at the beginning, then an error, and then no color at the end. So it was designed to be able to continue parsing, even if there's an error at some point. And what I found really cool is that when you want, if you don't use three-seater and you want to parse a language, for instance, if you want to parse Python code, you can use the Python AST module, or if you use Go, you can use the Go parser module. But it means that you need a Python runtime or you need a Go runtime to parse the language itself. And so if you want to parse multiple languages, you don't want to have a code editor and have a dependency on the Python runtime, the Go runtime, the Rust runtime, and so on. And so three-seater, it's just it's the parser that it generates is just some C code with no dependency on any external library. So you just need some standard C compiler and nothing else to build the parser and to parse code. So it's very easy to embed anywhere. Now, as I've told you, the main use case was designed to be used in code editors. So for syntax highlighting, code folding, we will discuss that at the end. Incremental selection. So incremental selection is like you don't want to select a full line, but for instance, you want to select only the arguments of a function, or you want to say to your code editor, select I'm in the middle of a function, select the whole function or select the whole class that these functions belong to. If you have semantic understanding of the code, you can do that. And of course, you can also do indentation. Also for code navigation. So if you use GitHub, you may have noticed that, since recently, like a year ago, when you browse code on GitHub, you can click on an identifier like a function name, and it will tell you where this function name was defined, the file in which it was defined. So they use three-seater for this, and there's a paper that you can check called Static Analysis at GitHub, where they explain how this works. But under the hood, it's based on three-seater. And what I will show today, you can use it to analyze code, like manipulate the source code with code. In this talk, I will focus on the code analysis part and not on the text editor part, right? I will show a bit at the end, like what you can do with three-seater in a code editor that supports three-seater. But the main focus is like, how do we use three-seater from the Python programming language to parse other languages? In this case, we will use Python to parse Python, but I will show that we can parse other languages. And how we can, there's a cool feature which is called queries, which are basically like regular expression. I mean, similar to regular expression, but for matching patterns in trees, like, and so how to find, function calls, which have specific arguments and so on in a tree. I will not talk about how to create parsers for a language because it's much more complicated than it's the most complicated part of three-seater. And as we will see, there are already parsers for a lot of languages, and incremental parsing, which is like what's used in text editor, saying reparse only this part of the code because this is the part that's changed. Well, it's more of a technical detail for text editor, so not interested in that today. Also, I want to mention that I'm not an expert in like a parsing programming language and so on. So thinking of you, Marco, if I'm not using words in their most precise meaning, please correct me.
It's okay, but I have a few remarks to enrich
Yes.
what you said, but it's very good for the moment. So the first element is you said at the beginning that you could use some regular expression at some points,
Yeah.
but there are also places where a regular expression couldn't work. For example, when you want to pair parentheses, this is the ability to pair parentheses is no more a regular language. And so this is an ability where you require AST typically to detect that every parentheses are well paired. So this is another, just to precise what you said earlier. And besides, so you say that in Python there is the AST module, which is very true. And actually, indeed, it only supports Python, if I'm correct. And AST module is quite recent. It's for Python 3.8 or something like this. But this module is meant to support additional grammars. So if you look in the Python AST web page, you could see that you could add some files that are called ADSL or something like this. So basically, you could specify other grammar for other language. I don't remember the file format, but it's written
Okay.
on the documentation page. So just to say that the library that you provide is valuable. There is no doubt about this. But if you want to use Python module, it should be feasible as well.
Okay. I didn't know that you could specify additional grammar in the Python AST module.
I will drop. But you are in the right page.
Yeah,
somewhere like this.
Yeah. Okay. I will check afterward.
Okay.
Okay. Thanks. So
Go ahead.
So let's get started. So to use tree-sitter, you need first the tree-sitter library for the language you want to use to manipulate code, and a parser for the language that you want to parse. So if we go to tree-sitter website, on their homepage, they have a list of language bindings. So this is all the language that you can use to parse other languages, and parsers, which are the language that you can parse. And as you can see, there are parsers for a lot of language and all of the popular language. So it's also, a benefit, I think, of using this library is that most likely there's already a grammar written for a language. So in this case, we want to use it from Python. So they have Python bindings that you can use, just like pip install tree-sitter, and you need to download. So in this case, we will parse Python code with Python. So we need the Python parser, which you can download. So you can just pip install, and so yeah, here I made a convenience function, but basically you just git clone the language definition. So you git clone the repository which contains, or you download the parser. Then you need to compile it into a shared library. So this is the part where you need a C compiler, but no external dependency, no anything. It's possible to compile multiple language in a single library. Well, here we don't really care. Even if we were parsing multiple language, we can use multiple shared objects. There's no issue with that. And then just build a tree-sitter language object. So nothing really interesting here, but it's a bit of boilerplate that you need to load the language. So here I'm instantiating the language object for the Python parser that I've downloaded from this repository. And you create a parser object and you set the language to Python. But if you want, you can create, another parser and instantiate it with JavaScript or something else.
It seemed to be unhappy.
Yeah. It's because I'm it's just the git clone which says like the repository is already cloned, but that's okay. That's okay. I'm just printing the error, so it's okay.
Okay.
So let's start with some simple examples. So I have a block of Python source code here. So in a string, and later on we will read from files. But here I just have a string, Python string, which contains Python code which says hello world. So how it works is that you just call parser.parse. Yes. No, okay. Parser.parse with the source code, and then you get the root node of the tree. And so here it's always the same. You take the root node of the tree, and what you can do on a node. So on a node, you can get the text of the node. So it's the text of everything that is below this node. So here, if we look at the root node, the type is a module, because every Python code, even here we don't define it, but it has an implicit module defined. So here the root node is a module, and the code of this module is print hello world, including the new line at the end. So we can take the text, we can get the type.
Sorry,
yes?
Maxime. For the moment, we agreed that this is exactly the same than the AST module. I
Yes.
understand. Yes. Okay.
Yes. So everything that we do for now, we could do it with the Python AST module. But also, if you were to just here use another language, just swap this for another language and here like input JavaScript, for instance.
Yes.
The same logic will apply, and we will see features specific to three-seater right after. But in this case, right, that everything of this could be done with the Python AST module.
And maybe I missed something, but where do you say that this is Python code that you are parsing?
It's a parser.set language.
Okay. Thank you.
So we can get the text, the type, and more interestingly, we can get all of the children of this node. So in this case, this node has children, which is a statement. And this is mostly useful for text editor, but we can get where does it start and where does it end in terms of bytes. And you can play with this and take the first children of the first children and so on, and get more and more nodes as you go deeper in the tree. It's a bit difficult though to visualize it by doing this. So one convenience function that they have is on the node that you have, it's the S expression function, which returns the tree written as S expression. So basically here, the way you read this is that you have a module which contains an expression statement, which contains a function call, which contains an identifier node, an argument list node, which both have two children, which are string. So this is one way, but what we can do, we can just walk the tree and here and plot it and draw it. So here I'm just using the network X library to build a graph and to draw this graph. I mean, the tree itself is already a graph, right? But here I'm just converting the concrete syntax tree to a network X graph that we can, then use all the network X function like to draw graph and so on, which is more convenient. So just converting the graph to a tree, and then we can draw it. And here it's much more clear what's happening, right? We have a module which has a statement, which the statement is a function call. There's an identifier, which is the name of the function we're calling, and then a list of arguments delimited by parentheses, which contains two strings delimited by quotes. Now these elements, maybe they are not very useful, right? The parentheses or the quote or the comma. Probably you don't care about this if you want, to analyze your code and so on. So they are called anonymous nodes in three-seater, and when you have a node, you have the isNamed function that you can call on a node, and anonymous nodes, so nodes like this, quotes or parentheses, they will return false. They are not named nodes. So you can filter them out by removing them. You see string, identifier, call, those have names, but they are just the elements themselves. They have no name. So we can filter them out using the isNamed function. So I'm just editing the tree to graph function, but to filter out named anonymous node. And now we can draw the tree again, and now we have something simpler and more useful. Then something else that you may have noticed is that if you look at this representation of the tree, you see that here we have nodes, so module node, statement node, call node, but we also have this kind of labels here, which are what called named fields, field names in three-seater. And those, they depend on the specific language that you're using. But when someone is defining a parser for a language, for instance, when the person so when we have these labels, we can use them. But those, they are language specific. So maybe you use the grammar for another language, there are no labels for specific nodes. But when you have them, for instance, for Python, we have them, it's useful. Now let's get to the most interesting part of tree-sitter, for me at least, which are the queries. So let's go to, if you go to the tree-sitter website, you have a playground, which is useful to play with queries. I will also show you how to do it in Python, but here it's more visual, more interactive. So first, let's start with some more complex code. So I have a code.py file, which has three functions. Sorry, add, hello, and main. And in main, I have some function call to the other functions. So I'm loading this file. I'm just parsing it. I'm dumping the tree. And am I missing? This need to be slide. And I'm dumping the tree. So here you can see that we have a much more complex tree. Now let's take this code and paste it in the playground. And here we can see that we also have the tree here, which is printed. And if we click somewhere in the source code, we can see where it is in the tree. So if I click on add here, it puts us in the function call, and add is the identifier. This is the integer argument, the first one. And if I click on float, we have 1.0, which is the float argument. So let's try to match. Let's say that we want to find all the function definition that we have in this file. So basically, we want to write a query which will return us all the function definition nodes. So this node, and this node. So the way the language works, and if you want more information, you go to using parsers and pattern matching with queries, and they explain the language. But it's pretty simple. Basically, it's like regular expressions. So if we want to match function definition nodes, we just write function definition, and then we put what's called a capture, or what I call a tag, that will be associated with this. So here, we can put whatever string we want, but let's just call this type function, right? And here we can see that it put in blue everything that matched. So of course it matched all functions. We can do the same in Python. So I have the same query here. I'm building the query, and I'm saying that query.captures, and I'm giving it a node. So in this case, the root node of the tree, and I'm printing it. And it says that it matched this function definition node, this function definition node, and this function definition node.
Maxime?
So yes.
So a question, when you write arrobas function, what does it mean?
Yeah.
Is
So
it
could be
apply the color style of function on every subtree that is rooted in a function definition node?
Yes. So first, this. So yes, there's two things. I will talk about syntax highlighting at the end of the talk. But in this context, it can be any string. It just means that in the playground, it's not useful. But for instance, here, if I will show you right after. But basically, in a single query, you can have multiple let's say captures, and yeah, and then you can so here I'm using this helper function that I made, print capture, but I get this tag. So you can use it to discriminate which expression has matched. So it can be arbitrary, but
if I understand well, so you define a kind of parsing rule to match every lines with arbitrary tags. So for example, DFAAD in your example, and then based on this classification, you apply some rules to color the code or do what you want.
Yes. In the context of syntax highlighting, here you will put something more meaningful like function, and then the code editor will know, okay, I put function in blue or whatever.
But correct me if I'm wrong. Is it more or less the equivalent of $1, $2, and the rest in regular expressions?
Yeah, it's a bit similar to capture to named capture groups in regex.
Yeah.
Regexes. Yeah, I mean technically those are not regexes, right? But in the spirit of it, it's similar, right? But we will see afterwards how we can use more of that. And so simple example, and what we can do here, I'm printing those, but it returns the nodes themselves. So let's just have a look at the captures. We have a node object, right? So then we can look at the chip. So I can take the first capture, and then I can take the children of this capture, and then I can go on and on. So it doesn't just return the text; it returns the node of the tree that match the expression. So simple example where we match all function definition. Now let's try to match the function names. So here, what the results that we want is we don't want the function node, but just the node which represents the name of the function, the identifier. So if we look at a function definition, so for instance this one, we see that we have one children. The first children is an identifier node, and then we have other children which represents the parameters of the function, and then the body of the function. So let's say that we don't want to match function definition, but we want to match a function definition which has a children which is an identifier, and we don't want to capture the full node, but we just want to capture the identifier node. So here I'm just putting function in there. It means that this tag, this label, will apply to it always applies to the node just before it. So here I'm not capturing the function definition, but just the first identifier child. And here we see that now it captured just the add, hello, and main. And to expand on what we said before, so let's just call this name. Here I can capture the full node function, and now in a single expression we have two captures. We have the name, which is captured with the name tag, and the full function, which is captured with the function tag. I could also use since here we have this named field, to be sure that I match the name, and maybe I don't think it's possible in Python, but maybe you could have an identifier which is not the function name, maybe in other languages. So let's just put name in front, and I ensure that it will match only a node which has the name. We can also have like wildcard names, wildcard nodes, a bit like regular expressions. The dot in a regular expression, so it's underscore, and basically this means match any node, and in this case match any node which is name. We can also remove name, and yeah, in this case it doesn't work because it will match all the other everything else. So we can get function names like this. Yes.
Maybe it's a premature question, but can you, in some sense, mix these kind of queries with the regular expressions, saying, for example, I want a function definition where the name is something that starts
yes, with... so that's the next slide.
That was my transition for you.
Yeah, thanks. So now let's say that we want only the function names. So let's roll back this to this. Only the function names, but that starts with a H, for instance. So in this case, hello, but that starts with a H. For this, we can use what they call predicates. And we will see this. One important thing is that predicates, they are not part of the tree-sitter library itself. They are part of the bindings for the language that you're using. Not the parser, but the bindings. So here we're using the Python bindings because we're using tree-sitter from Python. Doesn't matter which language we're parsing, but the the bindings that we use, they need to implement the predicates because the filtering is not done in the tree-sitter library. Most of the bindings and the text editors, they implement basic predicates, which are basically like equal, not equal, and match. And the match predicate says, well, take a capture and check if it matches a regular expression. So let's do this. So here we're matching all function name, but we want to refine this to keep only nodes, identifier nodes, which match the regular expression, which says this starts with the letter H. So to do this, you add another expression between parentheses, and predicates, they are defined like it's like is this called a hashtag? I don't even know what the name of this character, but let's say hashtag match.
Sharp.
Sorry?
Sharp.
Sharp, yes. And so sharp match. Then, so basically this it's it's arbitrary. It's just the name of the predicates. I think there's a list of predicates that you can use somewhere. Of the common predicates. Yeah, you have to look at the documentation of the bindings that you use. They I think they explain well, they probably explain somewhere what predicates you can use, but basically like equal and match, they are implemented by everyone. So here we want to use the match predicate. Then here we capture the identifier node with the tag name. So let's reuse this tag here. And then the regular expression that we want. So in this case, starts with H. And this doesn't work because maybe I need to, I need to put all of this in an expression. And now it works. We match everything that starts with H, right? And we can match things, that starts either with A or H, and because I need to, it starts with, yes. So any function that starts with, A or H and so on. So you can put whatever regular expression you want in this. It works on any node. Basically, it's matching the text of the node. So I could, say, take any function definition node, which has, I don't know, this letter or this particular substring inside the function definition. It matches the text of the node. So again, pretty, I think pretty useful, pretty powerful. And now let's see one last thing with queries, a bit more complicated. So let's say that we want to, here we have functions that have 2 arguments, no arguments, or 1 argument. Let's say that we want to match functions that have only 1 argument. If I write this, it's not going to work because it means match any function definition node which have at least 1 children, which is an identifier, but it could be 1, 2, 3, any number of it's not yes, any number of identifier, but what we want to match is not the function names, but rather the parameter node, which has any number. So this is correct, sorry. It means match any function definition which has a parameter node. So this one main has no parameter node. There's no, it just has a name, and it has a parameter node, but that is empty. And this one, they have a parameter node, but this one has 2 identifier, and this one has only 1. But this, it means 1 or more identifier. So if we want to enforce the fact that we want just node which have, the children is only 1 identifier, we can use what they call anchor. So it's the dot, which has not at all the same meaning as regular expression. The dot here means that we want an identifier node which is the first children of the parameters node. So there can't be any children in between. It has to be the first children. And then we can add a dot at the end, which means that it has to be the last children also. So here we want an identifier, which is both the first children of the parameter node and the last child. Sorry. And if we do this, we are matching only function which have one parameter. So in this case, the hello function. We can do the same to match function with two identifiers. For instance, I can add, another identifier here. And actually, this will match any function which has two or more, right? If I write A, B, C, or D, or whatever, it's still match, because here we can have any number of identifier nodes in between. So if we want to enforce the fact that we want just two identifiers, we add another dot. And in this case, it means there can't be anything in between here, anything in between here, or anything in between here. And now it will match only function with exactly two arguments. So can do this. And last one example is, let's say that we want to match function calls, but based on the type of the argument. And one important thing to understand here is that the type of the argument here, you see it says integer, it says like it's a float, and here it says like it's a string. It's the type, of the literal value, right? But it's not the type that is inferred by the language. Or for instance, in Python, most of the time, you know the type of a variable only at runtime, right? Just by looking statically at the code like this, you can't know. If I here, for instance, in the hello name function, if I look, or let's say, let's use something simpler, the add function, it takes two parameters, A and B. If I look at the type here of the node, A, it's just an identifier, right? It doesn't know if it's an integer, if it's a float, right? You can't know this. You will need to, run the code and trace the execution or something else, or just, run the code and call like something like a dot type in Python or something like this to know what is the actual type of the value. So here, what I'm talking about type is the type of the literal value in the source code, not the actual type at the runtime. Nevertheless, let's say that we want to match a function call which have two arguments which are both integer. So we can do the same as before. Let me paste this. So exactly the same as we did for function definition, but we replace function definition by call and parameters by argument list. And now I'm matching function calls which have two integers. And to demonstrate another feature of tree-sitter, which are what they call alternate groups. Let's say that we want to match the first argument is always an integer, but the second one is either an integer or a float. Basically, we can put between brackets multiple expressions, and it will match any of those. So first node has to be an integer, but the next node can be either an integer or a float. And in this case, it will match function which, if I put here a float, it will not match because we want the first node to be an integer. But the second one can be either an integer or a float. And I can maybe add, a string. And now, even if this is a string, it will match. And if I remove, it will not match. So any questions?
Yes, a question. So I understand that these kind of queries are very useful in a type language like C++ because the signature of a function depends not only on the function name, but also on the parameter types, which is not the case in Python. So I guess that here the framework is very elaborated to support any kind of languages, but we agree that this kind of queries won't be very useful in Python, or I missed something.
Yes, I agree. I agree that I will discuss a bit that afterwards, but I think so. Two things is that first, tree-sitter, yes, it's meant to be general for any kind of languages. which means that it doesn't have, deep semantic understanding of the language. Maybe if you use the AST module in Python, you will get, more understanding of what kind of function it is and so on. Not about the types, but maybe I don't know, maybe you will get more understanding, but it's also possible that if you were to do the analysis in Python, you could get more information about the types or so on. And also
so to be honest, just to answer this first point, no, I think that what you get in Tricitor is
the same.
rather what you have in AST is included in what you have in Tricitor.
Okay, so but for the second point, yeah, it's kind of a low-level tool, and which was not meant at first for this kind, and I will show an example afterwards, but to analyze code and so on, was meant for syntax highlighting at first. So it's both low level and also well, not designed for maybe more advanced use cases. Still, I find it useful for the fact that it's very simple to use. It has parsers for a lot of languages. So for a lot of use cases, it might be good enough. You just want to do this simple analysis of the code, find all of these functions which takes 2 arguments, and it will work right. If you want to do something more advanced, maybe there are better tools which are built on top of this or not. But I agree that it's not it's not one tool to replace all of
and
them.
my second question, so I can see in the page that you display that the 2 typical use cases of Tricitor are the syntax highlighting and the code navigation systems that you might want in your text editor. But you often talk about code analysis. Maybe could you elaborate a little bit more on what you mean by code analysis?
Yes. So, and I think there are tools that build on Tricitor which are better than this. I will show links afterwards. But one use case, for instance, is you want to find, security like anti-patterns or security issue in the code, and you can define a bunch of queries that match bad code. Like you can, for example, define queries that match code that is vulnerable to SQL injection, or this kind of match everything that calls the eval function in Python, because probably it's dangerous to call the eval function and so on. So try to match this, or you can use it also for linting code, right? Think of Flake 8 or PyLint or this kind of stuff. If you want to say, okay, you're calling you're writing code like this, and you shouldn't do this. Instead, you should call A plus B. Then it's easy to match. So that's one use case. I think that's what I mean actually by code analysis, right? I don't know if it's the correct word. Maybe static analysis or something like this.
No,
but that's what I.
It's right. No, it's a good idea, but so you indeed you could use Tricitor as a kind of firewall for code by defining your rules saying that this code is malicious or dangerous or whatever. But for example, if you take the example of firewalls like Snort, you have typical rules that are packaged and shared to help anyone to enrich its own firewall. Does it mean that we have the same kind of stuff for Tricitor for code analysis?
Yes, so there's a tool which is built on top of Tricitor. It's called SemGrep, and SemGrep, they so I never used it actually, but I heard about it a lot. And they have a SemGrep registry here. So their rules, they are it's a higher level language than Tricitor. They have their own language, but under the hood, it used Tricitor to parse the languages. And if we go to the registry, I guess that they have this registry of let's check what they have, like command injection vulnerabilities. Yeah, they have their own set of rules that are shared by people to match vulnerabilities in code. So it does exist, but for tools that are higher level. I don't think that again, I think Tricitor is a bit, I wanted to show the tool itself, because even if it's low level, you can do useful thing with it. But yeah, for production use cases, you may want to use something a bit higher level.
Thank you.
So and then we have when does it end? At
11:30.
Okay, so in 10 minutes. So let's end with this.
Questions included.
Okay, so I will go fast. Just a small use case that was useful for me. Actually, this is the first thing I did when I found Tricitor. Actually, it was a more complicated use case, but the idea is the same. Let's say that we just want to load a bunch of Python files and find which function calls which function and build a graph of the function calls. We can do this very simply. Again, there's a lot of issues here because we need to resolve module names, local variables, and so on. But still, very simply, we can do something that kind of works and gives some results. Obviously, if you want to do something more advanced, you need to handle more stuff. But my use case was a bit more complicated than this, but at work, we have this bash, this shell script, which called a command line tool, which execute a SQL queries to a database. And I wanted to find which SQL table depends on which SQL tables and on which shell script those queries are run. And because Tricitor can parse both bash scripts and SQL, the SQL language, I was able very quickly to build a call graph, a kind of call graph or dependency graph of the tables and the bash script. Anyway, very simple example here with Python. We want to match any function definition nodes, as we've seen before. And for any of these functions, we want to match any call node inside these functions. And we build a simple network X graph from this. So we start from the root node. We match all the function. For each function, we find all the call nodes inside this function. And then we just add an edge in the graph from the name of the function which contains the call to the name of the function which is called. And let's just run this. Where is it? Why don't? Yep. So here in this is the file I've used. So we have the main function which calls the other function, which calls the print function, and so on. Something a bit fun I did, I took a larger code base and I built a graph of the call graph of all the files in this code base. And it works because it's a code base which don't use much classes. It's because I don't handle classes here, it's just function calls. And this code base, it's a lot of functions calling other functions. And what's cool is that now that we have this graph, you can find easily what are the most the function which calls the most other functions. So for instance, we have this function which calls 30 other functions. It's quite a lot. You can also find which functions are the most called, and you can, for instance, find what is so I don't know if it's useful, but I found this fun. What's the longest path between the two functions? And actually, it's only 6 function deep. So I don't know. I thought that we would have longer call chains in this large code base, but interesting to find this kind of path in the code. To end, as we have already discussed, if you just want to parse Python using Python, then you can use the Python AST module. If you want to parse Go using Go, use the Go parser module, and so on. Tricitor is more like if you want to parse multiple languages from a single language. And there are higher level tools like SameGrep for finding vulnerabilities in code. Diffsitter, which never tried, but claims to provide a semantic diff for Git, or just diff between two files. So basically diff that understand that if a space has changed, it doesn't mean anything, or something like that. If you added a new line, it's not a meaningful change, and so on. And both of those are built on top of Tricitor. Now, I haven't discussed code editor, which was actually the main purpose of Tricitors, but two things that are enabled by Tricitors and are very useful, I think, in code editors. The first one is what's called Tricitor injections. For instance, as I've said at work, we have this shell script which call the BigQuery tool, which executes a SQL queries on the database. And by default, since this is a shell script, your code editor will parse all of this as bash, and you won't get any syntax highlighting inside the string here. But with Tree-Sitter, we can write a query, which I've put here, but basically which matches any command which has the name BQ, and I can say, I say everything that is inside the string of this command, of the string node of this command, highlight it as SQL code. And just by writing a query like this, I get SQL highlighting inside bash script, which very generic, doesn't depend on as long as your code editor use Tree-Sitter, you can do this, very cool. And the other one is code folding. So basically you can automatically define, folds. Basically you can, make section automatically for instance, here with this query, I say any line that starts with, not any line, but any command which has BQ in the name, then it's a section, and you can fold the code like this. Few editors that support Tree-Sitter. Unfortunately, it's not supported by JetBrains editor. So I'm a big fan of PyCharm, but PyCharm doesn't support it. Neither does Visual Studio Code. But it's supported by two big editors, which are Emacs and NeoVim, and the newer one, which is called Helix. And it's native in both Emacs 29, since version 29, and NeoVim, it's both native support. There's no external library. If you want to learn more, you can just go on the Tree-Sitter website, and these are the Python bindings. And that's all for me. Any questions?
No question, but it was cool for me.